Today we have the pleasure of having a legend as our speaker. And I guess before we get started, I want to welcome you all to the SETI Institute seminar series. This is a noontime series on Wednesdays. And we record these, and then they can be viewed afterwards, either through the SETI website or actually on YouTube. So just look up SETI Institute on YouTube. You can find these usually within a few days of the seminar itself. And because we record them, we ask that you try to save your questions till the end, so we don't have long delays when we're not picking up the questions on the microphone. So try to save your questions if you can until the end of the seminar, or if you just can't keep yourself whatever, can't wait. Maybe Mike will repeat the question if he remembers to. Anyway, a little bit about Mike. Many of you know Mike or have heard of Mike or have read Mike's papers. Mike, or Mars Mike, as I guess I've been told he's called, has the distinction of having been associated with just about every mission to Mars ever. Is that
Mine and nine, anyway.
And he's really has international training, formal training. He actually received his bachelor's in geology at the University of London, and then came to the U.S. and got a PhD from Yale University, and then did a postdoc for 2 years at the University of Western Ontario. And after that, and that was a little bit a while ago, he went to the U.S. Geological Survey, where he's been a planetary geologist ever since. So just to summarize a few of his activities, in the 60s, he participated in the Lunar Geologic Mapping Program and a variety of Apollo programs, and was even involved in training astronauts who were going to be walking on the moon, and to help them try to pick up rocks that would be of geological interest. In the 70s, he was a member of the Meridiani 9 imaging team and the leader of the Viking orbiter imaging team, and I guess helped to analyze more than 55,000 or so images of the surface of Mars. And he helped participate in the site selection for the 1997 landing of the Pathfinder on Mars. And he's currently a participating scientist with the Mars exploration rovers, the Mir rovers, that landed on Mars in 2004. Among his many distinctions, Mike has received numerous awards, and I'm going to list a few of these now. Sorry, Mike. He got the NASA. I've just summarized. He received the NASA Medal for Exceptional Scientific Achievement in 1997, and also the Department of Interior Meritorious Service Awards and Distinguished Service Awards in 1979 and 1988. He's received the Geological Society of America's G.K. Gilbert Award, and also National Air and Space Museum's Lifetime Achievement Award in Air and Space Technology. And finally, just recently, a few years ago, he was appointed an American Association for the Advancement of Science Fellow, so AAAS Fellow. And just without further ado, I will now hand the microphone over to Mike, and today he's going to talk to us about Mars, water, and prospects for life. Thank you, Mike.
Well, I'm a little embarrassed by the early slides that I'm going to show here, because I can look around this audience here and see people who are more expert on Mars than I am, and I wasn't quite sure what audience I was going to be talking to. So forgive the elementary stuff which is coming in the first few slides. Well, this may be the most active. Well, it certainly is the most active time in Mars exploration. There is many spacecraft at Mars, 3 active orbiting spacecraft, and I see some people here who are participating particularly in the back there, and who are participating in these orbiters. We're getting imaging down to 20 centimeters resolution. We're getting spectral data, infrared and visible spectral data, from which we can get mineralogy. There's gamma ray spectrometer, from which we can get compositional information, atmospheric sounders, and so on and so on and so on. It's a very busy time for Mars exploration. And as you know, there are 2 active rovers, Spirit and Opportunity, still working, although creaky, just like I am from old age. Phoenix lander worked almost perfectly and died as planned when the sun set at the start of the Arctic winter. Now, the main scientific thrust of Mars exploration is a search for evidence of past and present life. And this really is why the program at present is so vigorous, and why prior to this emphasis, the program in the 80s seemed to be somewhat stagnating. And there's also this this last goal to prepare the way for human exploration. But this, as I was just talking with Jeff Briggs here earlier, it always seems to be 30 years away. In fact, at the end of the Viking mission in 1980, it seemed closer, and even back earlier than that, in the 70s, human exploration seemed a lot closer than it is today. Now, I mentioned there were elementary slides at the beginning here. The size of Mars, there's a lot of Mars to explore. And the area of Mars is equivalent to the land area of the Earth. So there's lots of Mars. Surface conditions, Mars is cold, and the temperatures you can read up there from about, these are daily means, from about -60 to -120 C. And you can see the comparison with the south pole of the Earth. Now, those are daily means, and the actual daily range is quite large and gets well above, can get well above freezing, but those high temperatures only apply the top few millimeters of the surface, because the the daily mean is really quite cold. The atmosphere is thin and mostly composed of carbon dioxide. I'm just giving these slides because I gave this talk at USGS where nobody's interested in Mars, and I had to give a few basic facts. Now, Mars geography, you're mostly familiar with this. East and west hemispheres are very different. The eastern hemisphere is dominated by heavily cratered terrain, and the western hemisphere is dominated by a huge volcanic pile called Tharsis. And it's also dominated by numerous other features of just of striking geologic interest. The canyons extending radially from the center of Tharsis, which is about there, and very large outflow channels which flow up into the northern plains. The elevations on this diagram, the reds and the yellows are high elevations, and you can see that the southern hemisphere is higher than the northern hemisphere, and it's higher by about 6 kilometers. And this is a puzzle as to why the planet is so asymmetric. And the most dominant theory is that this was caused by a very large impact very early in the planet's history. The crust is also thicker in the south than it is in the north. Well, an effect which has had a major effect on Mars's geologic evolution is the cratering history. And this shows the cratering history, the cratering history of the moon. And the recent cratering rate, what we have here is age, and then the number of craters per square kilometers. And the recent cratering record is fairly simple, and actually the rate of cratering is really quite low and doesn't grossly affect the geology of Mars nor the geology of the Earth. But as you go back toward toward about 3.5 billion years, the cratering rate was much higher. Now there's a puzzle here, a major a conflict between two models as to what we're seeing here. One is that there was a spike here at around 3.8, 3.7, a huge spike in the cratering rate, and that prior to that, the cratering rate was much lower. The other theory is that these large cratering rates just extend back to the time of formation of the planet. That has some implications for life, because this is the period when life started on Earth, and we don't know what the conditions were like, and to what extent any life would be annihilated if in fact these very large impacts continued back to the time of formation of the planet. I'm not going to talk much about volcanoes, just to remind you that Mars is currently volcanically active, and that of course has implications for life, because it provides heat, it provides chemical gradients, and so forth. And most of the volcanism has been focused on in Tharsis, and you can see these the very large volcanoes that formed in Tharsis, and are probably continuing to form today. Now, the rate of volcanism is very much lower than on Earth, and the reason why these volcanoes are so large is that Mars crust is stable, and these volcanoes have been active for billions of years. The crust is also thicker, and that also is important for the size of the volcanoes. Well, this talk is about water, and we've known for a long time, since Mariner 9, that the Martian surface is dissected by what we call valley networks. This is about 100 kilometers across here. And this is one of the more densely dissected regions of the planet. But there are lots of densely dissected regions. And initially, when we saw these valleys, it appeared that they were much more open networks than typically on Earth, and the people speculated that they're not formed by precipitation, but they were formed by groundwater sapping, that is seepage of water from the ground. But now we're seeing these very dense valley networks that almost certainly must be formed by precipitation and surface runoff. We don't know whether it's precipitation of ice or precipitation of liquid water, but nevertheless, you have to have precipitation and surface runoff to get these kinds of dense networks. And the way they're distributed, you see here, they're mostly in the old terrain, but not all of the old terrain is dissected. There are large areas of this ancient cratered terrain which are undissected, which is another puzzle. But from this distribution, it's pretty clear that the rate of formation of these valley networks was much higher early in the planet's history than it was later. Now, if you have surface runoff and you have an uneven surface, and the cratered surface is very uneven, you should expect to see lakes. And indeed, we do see lakes. We see lots of lakes. And we see typically, we can see deltas inside depressions. There's a channel coming up from the bottom here, and you see this beautiful delta. Another channel here, you see the delta, the outline of the delta. And most of the sediment, a lot of the depressions in the uplands, craters and other depressions, have sediments in them, and the sediments are very finely layered. And this is fairly typical of what one sees in the flat-floored craters when you have sections exposed. The layering is so rhythmic and so persistent that it's unlikely to be just due to variations, to random variations. It looks systematic, and the chances are it's probably this layering is related to changes in the planet's climate, which would affects erosion rates and sedimentation rates that are induced by obliquity variations. And obliquity variations are variations in the spin axis of the planet. It has very large variations, and those are periodic variations that prevailed throughout the history of the planet. The Earth doesn't have those kinds of variations, mainly because of the stabilizing factor of the Moon, but Mars has very large variations in the orientation of the spin axis. Now, in addition to these valley networks that seem to form by precipitation, there are what we call outflow channels, which there are two examples there. This is fairly typical of what one sees on. Oops, I'll get used to this in a minute. This is fairly typical of what one sees on some of the large valley floors. You can see here, this is 20 kilometers across here, so we're about 100 kilometers across here. The valley, the erode starts, or the channel starts at a fault, which is a fairly common occurrence, and it has no catchment area. The water appears to have come out of this fault, and in major quantities, and left its and sculpted the region downstream from the source. These valleys or channels are younger in large part than the valley networks. The branching valley networks are almost everywhere in the ancient terrain, and typically greater than 3.7 or 3.6 billion years old. And they clearly imply a change in surface conditions about that time. Unfortunately, as typical in science, it isn't black and white, because we do see younger valley networks. They're rare, but nevertheless they are there. So one cannot ascribe all the valley networks simply to this major climate change at this time. There's got to be some other mechanism at work at a later time. The outflow channels formed at a later time, mostly in this time period here, from 3 to 3.7 billion years ago. However, there are several really quite substantial geologically young outflow channels in the order of 10 to 50 million years old. And those ages are derived from counting small craters. And so these, since these appear to be eruptions of groundwater, they imply that the presence of groundwater below the cryosphere, below the frozen zone today. Now, if you have precipitation, and if you have these large eruptions of groundwater, you've got the groundwater the precipitation has to go somewhere. And if early Mars really had an active hydrologic system, as implied by those valley networks, the lower areas must have contained large bodies of water. Unfortunately, when you go back in time to that period, it would be very difficult, because of the effect of cratering and high erosion rates at that time, to uncover evidence, convincing evidence of those large bodies of water. Now, there's a much better chance that with the younger large floods, you may be able to uncover evidence. And what we see here is we're looking down on the North Pole, and these contours outline different basins within at high northern latitudes. These are not shorelines. I've just drawn contours at the overflow points between the large northern basin and another basin here, and between these two basins. But several shorelines have been proposed around these low areas in the northern plains. The canyons are very puzzling, and also have implications for the water story. You can see how big they are from this diagram. And the origin of the relief appears to be largely structural, that is, largely caused by faulting. And you can see here a pretty good example of a fault scarp. Typical of a fault scarp are what are called triangular facets on the spurs. You can see them here. This is very typical of terrestrial fault scarps. So the evidence seems to suggest that this is a downfaulted block, and then other processes have taken over in eroding and modifying the scarps that were formed by faulting. And you can see a large landslide here, but there's also other mass wasting processes and probably fluvial processes that have taken place. Now, one of the most puzzling aspects of the canyons are the presence of mounds within the canyons. The canyon here is about 200 kilometers across, and what I'm talking about are these sort of mounds here. Now, when you look closely at these mounds, they're very finely layered. And not only are they finely layered, but they're formed dominantly of sulfates. So there's a puzzle as to how these piles of sulfate are formed. Now, this is the evidence of the sulfates. This is a slide from a French instrument headed by Bebring, and these aqua-colored, you can see the canyon here, and these aqua-colored spots are these very sulfur-rich mounds. And these, you can see over here on the edge of the map, this is the Meridiani Sulfates, and throughout this area there's an abundance of sulfates. Now, these sulfates, I mean, when you see them on a map like that, you get a false impression. These sulfate mounds are huge. This image here is the Grand Tetons, and that's about the same size as this mound of sulfur here, of sulfate, not sulfur, of sulfate. And this is data from, I think it's CRISM, a spacecraft which is there now, an instrument which is there now, and you can detect the different sulfate minerals within this huge layered mound. And you note here that these sulfate minerals are hydrous sulfates. Again, another indication of water is playing some major role in the formation of these sulfate mounds. Well, the age of these canyons is pretty uncertain. They could have started very early in the planet's history, but faulting has continued throughout most of the planet's history. And the canyons transition eastward to very large outflow channels. I showed some pictures of outflow channels area. These canyons merge to the east with very large outflow channels. So water has played a major role in the evolution of the canyons. Now, I mentioned that we saw earlier one of those slides where you could see a fault and a large channel, a large outflow channel emerging from a fault. Well, the canyons themselves appear to be largely fault generated, at least the relief. So it's not unreasonable that the formation of these huge faults that form the canyon could have also resulted in massive eruptions of groundwater. And of course, the canyons have contained many closed depressions, so one probably ended up with lakes within the canyons. Now, that doesn't explain the origin of those mounds. The origin of the mounds is really very puzzling. Are they simply evaporation of intercanyon lakes? Could these several kilometer high mounds of layered sulfates form simply by evaporation? One could build a model such that as the canyon floor is falling, and you're getting successive eruptions of groundwater which evaporate, and then the sulfates build up. That's a possibility. But they could also be trapped aeolian deposits that formed elsewhere by alteration of the and evaporation. And a third possibility, which is not widely accepted, although it has a strong advocate who I won't name, is that these sulfate mounds are just remnants of the material into which the canyons are cut. So the message here is that hydrated minerals accumulated in the canyon, the chances are pretty good there were lakes in the canyon. How deep those lakes were, whether they were, how long they lasted, all those details are sort of unknown. Well, I'm going to quickly go through what was found at Meridiani. This is the, as you know, Meridiani landed on an extensive on extensive sediments, and we were able to go down into Endurance Crater and look at what those sediments were like. And this is a close-up inside Endurance Crater, and the sediments turned out to be largely sulfates mixed with altered basalt. And there was very little direct evidence from the morphology of the sediments of water, but except at the top of the section in Endurance. Here there were indications of actual ripples and so forth that would and other structures that would be formed by the presence of liquid water. Most of the section was aeolian deposited, and so there's a playa source or some source of sulfates nearby, or perhaps in place there, that moved the and the sulfates were moved around by the wind and deposited in this region, over an extensive region, because the section that Opportunity is sitting on extends for something like 600 kilometers across. There's also evidence of movement of water after the sequence was deposited, and that's you see evidence of dissolution of minerals and an incrustation of minerals, so that the water was moving up and down in the section after the material was deposited. And the chemistry and mineralogy is given here. This has been derived from the mineralogy. The various minerals shown here have been derived from the chemistry of the soils, not from direct detection of the minerals. But you can see the minerals on this side tend to be rock-forming minerals, and these on this side tend to be more sulfates. So it's a mixture of altered basalt and sulfates. And I mentioned the movement of water up and down the section. The green here is chlorine, and this is a vertical section, and the purple here is bromine, and this appears to be movement of the volatiles, the soluble materials up and down the section. Spirit was a very different place, and we landed on these lava plains, and they were all in basalt, and we were very disappointed when we landed here, because the last thing we wanted to do was sit on a basalt plain, because our main interest was the water story, because of its implications for life. And so it was sort of a dissension. There was some sort of dissent within the team, because some of us wanted to get out of there and go as fast as we could to the hills, where we hoped there'd be something different. And there were others in the team who wanted to analyze every rock and every soil that we on the way. And so there's a hero in this story. Dave here, Dave DeMarais, he put together a plan that enabled us to get to the hills within a reasonable length of time, and yet satisfied the people who wanted to stop and analyze every basalt that they saw. And Dave sold it to the team, and the rest is history, as they say. Well, the path over to the hills, you're all familiar with this. And when we arrived at the hills, it was incredible, because you could just sort of step from these boring lava plains into these incredibly different stuff, all weathered, weathered and oxidized and so forth. So there was an alteration, total alteration change. The younger basalts were almost completely unaltered except for a very thin rind, and the rocks in the hills had obviously been affected by fluids, by hydrous fluids, and we got all kinds of peculiar structures that we saw immediately we crossed the line. And and as you know, we went up into the Columbia Hills and encountered a number of strange things such as sulfur-rich soils, and I still have not seen a good explanation. Perhaps Dave has a good explanation for the sulfur-rich soils, but clearly there's been mobility, there's been weathering, extraction of acid by acid fluids, and concentration of sulfur near the just below the surface. We also saw another peculiar soil. These are silica-rich soils, and this was somewhat fortuitous initially because the front wheel was locked and exposed the silica-rich soils, and these appear to be formed either by extreme leaching of acid fluids or deposition from more alkaline hydrothermal fluids. And I don't know whether that's been settled yet in the team. I have been retired now, and I've somewhat distanced from the team. Not settled. Okay. Oh, Jeff. Yeah. So now I'm moving a step, moving on in time, and one of the instruments that's currently there now is a CRISM, and what it does is detect the spatial distribution of minerals. It gets what's called an image cube, in which you have a two-dimensional picture, but each pixel in that picture is a spectrum, and so you can get from the spectra you can get the distribution of the of minerals across the surface. And basically, this is a picture, an image, not an image, a diagram showing how the thing works. As you're flying along in orbit, you look forward and keep on imaging the spot that you're after, and you build up an image of what's in the field of view of the instrument. And what they're finding is really quite remarkable, in that there's a very great difference between that old cratered terrain in which we had all those valley networks and lakes and so forth, and the younger plains. And much of the old cratered terrain that dates back 3.8 billion years ago is rich in hydrous minerals. And you can see that that transition is illustrated by the Neely Fosse here, which is about in that region, 3.8, 3.9, 4 billion years. We don't know the exact dates of these things. But here's a close-up taken with high-rise of that region I just showed you. And the place where this image is from is here. And as you go up through the section, this is Noachian, means ancient cratered terrain. Go up through the ancient cratered terrain, you hit olivine-rich and unaltered younger strata. So a transition took place here. That transition I've been talking about around 3.8 billion years ago, where hydrous alteration was very common until, and as you transition upward, hydrous alteration becomes very uncommon. It's the same transition that we saw in Gusev crater, where we left the plains, which were hardly altered, and went into this very highly altered older terrain. Now the minerals suggest that there was alteration by surface waters in the in this temperature range, but other minerals are indicative of hydrous alteration at higher temperatures. So the bottom line is that there's a major change around 3.7 from warm, wet, and we don't know what those two warm and wet mean, those two words exactly, to mainly cold and dry conditions as suggested by the distribution of the valley networks. So let me change topics a little because I'm running out of time here and talk about the amount of water that's present. We have all this evidence for hydrous alteration, valley networks and so forth. Early on, well, was all that water lost early on, or is it at the planet today? Well, this is looking down on the North Pole. There's water ice at the North Pole, but nowhere near enough to explain what we're the extensive alteration and so forth that we see in those old terrains. There's also ice at mid-latitudes, going down to about 32 degrees latitude. Ice in the ground has been detected by ground-penetrating radar, and this is two examples of that. In these latitudes, at all steep slopes, there appears to be ice aprons around the steep slopes, and the ice has moved, and you can see images such as this, which resemble glaciers. And so, we know there had to be a lot of water there. We see all the channels and the valleys and so forth. And the atmosphere today contains only minute amounts of water, and water ice is at the surface only at the poles. But there must be a large inventory of water somewhere, because all the calculations as to the loss rates that are over the last 3 billion years suggest that the loss rates are rather minor compared with the amounts of water that you need to form all those valleys and do all that alteration and so forth. So most probably the water resides as ice at probably down to kilometer depths at the higher latitudes, and groundwater at greater depths. And I mentioned earlier that you do see young outflow channels, and that is indicative of ice below the cryosphere. I mentioned obliquity. This is the history of obliquity. The obliquity shown here against the last 10 million years. It's very difficult to know specifically what obliquity occurred at what time prior to this period. However, there are periods when Mars obliquity, probably some few percent of the time since in the last 3 billion years, Mars has had obliquities as high as 80 degrees. So the spin axis was tilted over as far as 80 degrees. And of course, as you go around the sun's beating in summer on the summer pole for an Earth year almost, and then the ice would accumulate on the opposing pole during the winter. Now, this is important with respect to the availability of present-day water. We see gullies on many steep slopes, and this is something of a puzzle. The gullies appear to be cut by water, and the most likely, I think, the most likely explanation is that during these periods of high obliquity, you have ice accumulating during the winter when the slopes are shaded, and then at the opposing season, the sun beats down on this ice, and you get melting ice at the base and formation of gullies. So let me talk a bit about origin of life on Earth. I just have 3 slides here. This is an incredibly controversial issue as to when life started on Earth, but there's no way I can go into it in detail. But one piece of evidence is what you see here. Bill Sharp has suggested that fossils are as old as 3.46 billion years, have been found in Western Australia here. There's also other evidence of light carbon. Life fractionates carbon, so that organic carbon tends to be lighter than inorganic carbon, and it's been suggested that some old apatites, and these are phosphate minerals, in some ancient 3.85 billion years old rocks in Greenland must be formed biologically because of their light isotopes. And almost every aspect of this work has been questioned. The age of the anises has been questioned, and the presence of the carbon inside the apatites has been questioned. Although recently the carbon has been detected inside the apatites by Raman imaging. There are the third slide is probably most of the people in this room recognize this is the tree of life. It's an old version, and most primitive life forms are high temperature forms, and so there's some suggestion that two possibilities to explain why most of the life forms on Earth are close to the root of the tree that I just showed. Live in very high temperature environments. One is that we're seeing that the life originated in high temperature regions such as ocean vents, and the other is that the life originated on Earth in regions where of more modest temperatures, but was almost annihilated by large impacts. So the only things that survived, the only organisms that survived, are those from high temperature vents, and so all subsequent life evolved from those that survived. Now, what? Why did
you leave out the possibility that Earth was seeded from Mars?
Well, I have that actually. Oh, sorry. Well, Mars and Earth exchanged materials as a result of impact. And we know that. We've got 35 Martian meteorites on Earth. You remember the curve of cratering rates. The cratering rates on early Mars were much, much higher than on Earth, than recently. And so the exchange rates were much higher on early Mars, higher by orders of magnitude. And also modeling studies have shown that a small fraction of the ejecta from Earth and from Mars, it can go both ways. It's easier to go from Mars to the Earth. But a small fraction of the ejecta from Earth could reach Mars unsterilized. So there's a third possibility. Carl?
It could go the other way, too.
Yeah, it could go, yeah. So if some form of life started on Earth today, did start on Earth in that period, that more clement period, or Mars was successfully seeded from Earth, could some form of life have survived the transition to the predominantly cold, dry, hostile Mars that we see today? And it's possible, of course. Many microbial communities extract energy from chemical gradients produced by geologic processes such as hydrothermal activity and evaporation. Mars is a volcanically active planet. It has been all its history. It could have produced well, various minerals would have been produced. We know there's water. There's an interaction between the volcanic activity and water, produce a range of minerals from which with redox gradients and so forth that organisms could extract, from which organisms could extract energy to survive. And There are claims of microbial communities on Earth living kilometers below the surface, independent of any photosynthesis. And so it's possible, it's certainly possible, I don't know how plausible, but it's certainly possible that microbial life could have colonized the subsurface. I've given evidence that there was, that we almost know for certain that there's liquid water down there. We know there's lots of ice, there's volcanic heat, there's hydrothermal activity, Kelvin gradients, everything that one needs to survive. We don't know of course, what happened, and it's almost impossible to probability on it because we only have a statistic of 1. There's no way of hanging a probability number to that. I'm not going to go into that. It's old hat. So the story. Mars, at the time that we think life started on Earth, had hospitable conditions, seemingly. There's more and more evidence as each mission comes and each spectrum comes back from the planet. That appears to be a stronger and stronger case. That early Mars had conditions that seemingly are more hospitable to life. We don't know exactly when when life started on Earth, but there is this period here where there was an interchange of material between the two planets. Whether life started on Mars and seeded the Earth, or life started on Earth and seeded Mars, we don't know. Or whether there's what they call a second genesis, that life rose independently on Mars and on Earth. And the only way we're going to find out is by going there with the appropriate instrumentation, and we're working hard to do that. Thanks.
Very nice talk, Mike. To follow up on Carl's question/point, the first possibility you said was life never existed on Mars, and that seems pretty difficult. I can see it. Maybe it was never established on Mars, but that rocks would make it with viable organisms, and they might not have gotten there till after the clement conditions arose, but can you see a way that they would not have gotten there and there wouldn't have been microbes until they were brought by Viking or whatever in small numbers?
Yeah, I think you're right. They during the last few billion years, I mean, there's 35. I once calculated that on Earth we get about 1,000 kilograms of Mars per year. Yeah, it's a lot, and that calculation is based on the ratio of falls versus fines, and the proportion of Martian meteorites to regular meteorites. So now, it's much more difficult to go the other way. But if it's a factor, even if it's a factor of 10,000 more difficult, we've got billions of years to do it. So I think you're right. Certainly, the terrestrial organisms went to Mars, whether they survived the trip. According to the calculations by Gladman, you get some small fraction gets there within a few years, and we know from experiments here on Earth that you can get bacteria to survive a few years. So yeah, it seems almost certain something got there. Whether it could survive when it got there. Carl.
Mike, thank you very much for a great talk. What do you think is our present state of knowledge about a subsurface liquid aquifer on Mars today, and what do we need to do to improve that state of knowledge?
I think it's almost a dead certainty that there's an aquifer down there, and that's based on these young valleys that start at faults, and particularly well, there've been crater ages. You know, the crater ages, who knows how would they? But they're getting crater ages of 10 to 15 million years. Now that's just yesterday, on the eroded surface caused by the channels come out of these faults. I mean, and now whether those channels, I mean, there's another alternative. The channels could not be cut by water; they could be cut by lava. But nevertheless, I think it's all the other evidence of water. There's water everywhere. Certainly, water ice is everywhere. So, and we know that Mars is active. So, the combination of having a volcanically active planet and ice everywhere, it's going to happen. You're going to bring water to the surface.
Mike, this is a question about a return sample from Mars. Apart from the issues of the difficulty of collection, and apart from finding the one rock that has a fossil in it, what kind of a sample do you think would be the most important to bring back that would tell the most of the story of Mars?
Well, first, do you focus on recent life or do you focus on ancient life? To me, you should focus on ancient life. Go to the ancient terrain. The next step would be to look for organic carbon. I mean, do this. Don't bring the samples back if it has no organic carbon in it. So take instruments with you that tells you whether there's organic carbon there. And it would seem to me that if you've got an ancient sample with hydrated minerals and organic carbon in them, grab it. Bring it back.
So was water, do you know whether it was very acidic or not, given there's so much sulfate?
Well, well, there's evidence of both acidic and alkaline waters. I mean, Dave could answer this question better than I could. I mean, the weathering, these weathering lines, and that we see are certainly formed by, almost certainly formed by acidic waters. And the presence of jarosite seems to indicate that the sulfates in the at Meridiani were formed in acid waters. But then you have other minerals. They're finding more carbonates and some of these other clay minerals that formed in more neutral waters. So I suspect there's both, just like on Earth. I mean,
you mentioned that the Mars is very much alive tectonically. What are the possibilities of extracting information about the current stress field?
Current stress field. I'm not the one to ask about that, but there's I can't. I shouldn't answer that question because my background in geophysics is not so hot. But you can. A lot of work has been done on that because because Mars's surface is so uneven. One can calculate the stresses just created by the topography itself, and they're substantial. There's Bruce Bannett of JPL and Roger Phillips have mapped the stress field around Tharsis and compared the stress field with the deformation that's seen. There are two kinds of deformation. There's the radial faults, which appear to be due to tension, and then there's circumferential ridges that are due to compression. And when they do the calculations of the present topography and gravity field, they find stresses that are consistent with what we observe. The stresses may be important, but the question may be important from a water point of view, in that it's a puzzle as to why the floods are so large. And one possibility is that you have this aquifer down there, but it's under tectonic stress, and that pops out the water when it exceeds a minimum of some kind.
What are the dangers of contamination, both from the spacecrafts we have sent and from possible human exploration?
Well, Now, there are very strict protocols as to cleanliness and sterilization as far as sending the robotic spacecraft, which are sent to Mars. And I happen to be on the Planetary Protection subcommittee that looks into that. And what they do is they classify each mission. There are certain levels of cleanliness that are required according to the type of mission. Obviously, in land, you need much more cleanliness and sterilization protocols to follow than if you're in an orbit. As far as humans concerned, I feel very passionate that we have to answer the question of whether there's life on Mars and do some characterization of that life before we attempt to do human exploration. I'm afraid that if we jump in and do human exploration, we're going to screw up the whole planet, and it would be such a sacrilege to do that. You know, to send people there before we've really resolved the issue of whether life ever started. So, you know, but fortunately, you know, we're still 30 years away, and 30 years from now, we'll still be 30 years away. So,
would there be a danger of contaminating Earth by microbes that we're not able to defend against?
Well, yeah, that's an issue with sample return. It's a big issue because one has to ensure containment and at Mars, and ensure that the thing doesn't crack. You know, there's containment requirements all the way in to the containment lab in Houston or wherever, or in France, wherever the samples are returned, and the sort of agreements are that the samples won't be released until we're assured, you know, at least unsterilized samples will not be released until we're assured that that they're not a danger.
Jack is right. The planet has already been contaminated. We don't have to worry about it.
Yeah.
No. Okay. Yeah, Mike, I just wanted to comment about the Archaean record of life on the Earth, and that is that there's recent data that have really firmed up the notion that it's at least as old as about 3.7. First, they've discovered now, Allwood has described an ice stromatolitic reef complex that is just, you know, a whole complex, not just one stromatolite, but shallow water, deep water, the whole complex. It just very strongly resembles, that's Strelly Pool, so that's about 3.4.
What's it low? Is it at Stanford?
He's got another line of evidence that biofilms in shallow water environments that disappear when you get below the photic zone. All of this at 3.4 to 3.5. And as far as the Ishua, the Achillea stuff is still controversial, but there's Ishua that's at 3.7 that Rosing has found beautiful organic, rich shaly layers and the isotopes and the whole story. So, yeah, there is, and then even Schopp's filaments, the ones you showed are controversial, but there's finer micron-sized filaments that a number of people agree are probably biogenic. So I think, you know, it's totally consistent with what you're showing here, and it's new stuff that I think has firmed it up. The other comment I wanted to make was regarding the type of rock to look for on Mars, and that is that 70% of the organic carbon in the crust of the Earth is sequestered within shales, or phyllosilicates, clays basically. And also at Meridiani, that big silica wedge you showed is actually thought to be aqueously formed silica. It's actually a weathering product evolving along with the iron and the magnesium that's shown in that pie diagram. So I think an ideal thing to look for would be a phyllosilicate-rich deposit that maybe is impregnated a bit with silica. These are logical outcomes of weathering, and on Earth both are just get high score for preservation, and concentration of organics and preservation.
I think your comment about not sending humans there until we settle this question of life is a very interesting one. Because it could lead to kind of an open-ended program, Mars exploration, trying to find evidence for life or not. And it raises an interesting question, at least in my mind, maybe for you and others in the astrobiology community, is we are still groping with this fundamental question of whether life actually got started on Mars or not, obviously. So what would it take, in yours and maybe others' opinion, in terms of future missions and observations to settle the question one way or the other?
Let me tell a little, in response to that, let me tell a little story. I was asked to give testimony before the what did they call it? The commission that was looking into the Bush's commission to look into the future of the NASA, the Mars I forget what they call it, the vision for NASA. Okay, so and they had a meeting up in San Francisco, and I was asked to go and give a presentation, and we were asked to write our presentation before we gave it. So I wrote up, and I more or less said what I just said a few minutes ago. I was asked to not say that. And by a NASA official. And I said it anyway. And but one of the questions from the panel was your question that you just asked. What would it take to resolve the and make sure that or at least have a reasonable chance of, concluding that the life really didn't start on Mars. And I didn't, what I said was that we need sample return, and we need a few sample returns. And so they said, well, how many sample returns? And if you recall, just a few years ago, there was I think it was Complex, studied sample returns, said they needed 10 sample returns. These things cost about $10 billion a piece. It's $7 billion a piece. So it's a lot of sample returns, a lot of money. And I said, well, that's what I said. I said, one recommendation was 7 sample returns. I didn't think it would take that much. But I do think a few sample returns from key places. And as David just outlined, we're able to pick the places much better now than we could 10 years ago with all this mineralogy and detailed mineralogy and detailed imaging and we can pick the places much better. And also we can 10 sample returns, but we have rovers, so we can go and get 100 samples with each sample return. So I think a few sample returns would be sufficient. To drill? Nah, I don't think drilling helps much. I know that's a heresy here, but
Questions, and let's thanks Mike one more time.